Hi, welcome to this series of videos for pupils studying Unit P5 for OCR 21st Century Science. This is lesson 3, all about resistance. We're going to look at what causes resistance, its definition in units, and how it affects current. Now we know so far that a current is a flow of charge, and a charge such as an electron, which is attracted in a wire towards the other end of the wire because a positively charged terminal or battery has been connected to it. Now, if there were nothing else in the wire, then the electrons would zip down towards the positive charge. But unfortunately, in a wire, what we have is a lattice of atoms from which the electrons came. So strictly speaking, they're positive ions. And on its most simplest level, these electrons, which are in the gaps, cannot just zoom down to the other end of the wire because they will encounter the positive ions. So what we're really saying here, that resistance is essentially a measurement of how hard it is for these electrons to get down to the end of the wire. So let's imagine the path of one electron here, which is ping-ponging around between those positive ions in order to get down there. So we define resistance as the opposition to flow of charge. The bigger the resistance, the smaller the current that's going to flow, and vice versa. Remember, in an ideal situation, electrons could just whiz down the wire, but there's nothing in the way. Unfortunately, the reality is that electrons will make multiple collisions between themselves and the other parts of the material that they're in. So we define resistance as opposition to flow. The units of resistance are called ohms, and we'll come on to the reason how we define an ohm in the next video on Ohm's law. But the symbol for resistance is R, and the unit of resistance is called the ohm, normally represented as a horseshoe or an omega from the Greek alphabet. So resistance is caused by things getting in the way, and therefore the bigger the resistance, the bigger the opposition. I think the name speaks for itself. If there's a big resistance, then it's harder for something to happen. So we're just going to look to think about what that does to currents flowing. Maybe you've already worked it out, and we'll use the idea of the rope model to think about it. So I introduced the rope model last time. I wonder what the rope model would do in order to reflect resistance. Hopefully you've worked it out. It's essentially the grip on the rope. Now, the tighter the grip on the rope, the harder it is for the battery to push the electrons round or to push the rope round. And so the speed of the rope moving, or the amount of current passing, gets less. So tighter grip equals more resistance. So more resistance equals less current. So the relationship between resistance and current is that if you increase the resistance, you will decrease the current. So that might be the person who's gripping the rope, who's offering the resistance, grips tighter. Or you could imagine, what if we had two people gripping the rope to double the amount of resistance? You can see then that if this person pushes the rope with the same force, with the increased resistance, the rope is going to move much more slowly, so the current is reduced. So the effect of resistance on current is that as you increase the resistance, you decrease the current. Remember, I is a symbol for current. Graphically, that's like that. And that's an inverse proportion relationship. But again, for now, just think about that idea of increasing resistance, decreasing the current. I'm just going to point you back to these three key ideas now: voltage, current, and resistance. Voltage, if you increase the voltage, you get more current. If you increase the resistance, you get less current. Notice that it's always current that gets affected, or is the dependent variable. It can't affect the other things. They affect it. Okay, thanks a lot.